Good morning, student. This is Dr. Vandana Kobragade. Today we are going to study the next property of our unit number 5. Mm, That is our unit is the colligative property of dilute solution. We have studied the different colligative properties in last two lectures. That is osmotic pressure, lowering of vapor pressure, then elevation in boiling point, depression is freezing point. And we also deal with in last lecture we have seen the thermodynamic derivation of the colligative property. Today we are going to discuss the next point, that is Cotter's method for determination of elevation in boiling point and molar mass of solute. Okay, now FG Cotter's in 1919 has invented the actual method for determining the elevation in the boiling point. He has invented this apparatus. He has developed this method how to determine the boiling point of the solute and the solution and the solvent. So here we have taken a boiling tube. It has a side tube, and in the boiling tube we have taken the solvent, which and the solvent whose melting point we have to determine. This is the hood tube where we can insert any apparatus. Here we can insert the Beckmann's thermometer. Beckmann's thermometer is a specialized thermometer for determining the high high temperature as well as the low temperature of the pure of the particular solvents. Okay, now here you can see the solvent is present. Here the solvent we have taken whose we have to determine the boiling point. Then inverted funnel is kept here, and in this boiling tube, and the inverted funnel is kept in such a way that the vapors of that boiling solvent will be accumulated along this bulb of the thermometer. Means the all the vapors will be spread over this bulb of the thermometer. Now porcelain pieces are also kept here, and heating is provided from this downsides, from this lower side. Okay, now the what is the use of this side tube? This side tube is used for condensing the extra vapors of the solvent. Okay, Beckmann thermometer here, and here are the numbering. You can see the scale is there. This is means this is the graduated boiling tube is present here. Okay, now let us see what is happening here. We have to solvent is placed in the boiling tube with a porcelain piece lying in it. Means first we have to keep the solvent here, and then the porcelain pieces we have to drop there. Then the tube is heated in with a smaller burner. Then we need the smaller burner. We don't want high heat. We need some graduated heat or moderated heat or slow heat. Okay, when the solvent starts boiling, the vapor of the liquid continuously spread around the thermometer bulb. You can see here around is drawn here. You can see that means all the vapors will be spread over this along this bulb of the thermometer. Okay, now so that as it the vapors will be surrounded around this thermometer bulb, it records the temperature, and that temperature will be considered as T0. T0 will be the temperature of the pure solvent. Okay, now we have to add some solute in this solvent. Now how much solute is added? We have to consider W amount of the solute is added in the solvent having weight W. Means we have to consider small W amount of the weight of solute which is added in this solvent, and the weight of the solvent is considered to be capital W. Now again the same procedure we have to apply. That means we have to apply the heat from this lower side. That it should be in the moderate level. That means no high, we don't want high heat, we want the moderate heat, so that the proper heating should be done for this solution, and the vapor are produced, and that vapor will be surrounded over this bulb of this thermometer. Okay, and that temperature will be recorded. That boiling temperature of the solution we will consider as T. Okay, now as you all know that elevation of boiling point is occur when we add the solute in the solvent. Okay, that means whenever we add the solute in any solvent and records this at boiling temperature, the temperature is found to be more. That means if the temperature of the solvent is T0, and the T is the temperature of the solution, then naturally the boiling temperature of the solution is more as compared to the solvent. Therefore, we have this equation delta TB is equal to T minus T0. Now here we have considered the weight of the solvent. Obviously, you will have the question how the weight of this solvent should be considered. Now you know that we have taken the some amount, that means volume of this, we have taken the some liquid solvent, that means that should be in the ml, but we have to take the weight of this solvent. Now every solvent has the density, okay, that means if whatever the solvent we will consider taken that have the density, that is rho. Now when you all know the formula of density, that is mass upon volume, okay. Now we want the weight of the solvent, so therefore mass will be considered as W, that is the weight, and volume is whatever volume we have taken of that solvent, that is it may be 20 ml, 30 ml, whatever, that is the volume, okay. Weight in gram and volume in ml. Therefore weight can be calculated, W is equals to rho into V, okay. In this way we can calculate the weight of the solvent. Okay, the volume of the solution is converted into the mass by multiplying with the density of the solvent at its boiling temperature. Okay, let us see the next slide. This is the Cottre's method, and this is the apparatus. You can see the Beckman thermometer is here. This is the inverted funnel. The burner is providing the heat from the lower side. Graduated boiling tube is we have taken, that is graduated means the mark should be, scale should be there. This is the side tube of the boiling tube, and through the side tube we have taken the condenser. In the condenser, water flow is flown from this one tube to another tube, so that the vapor which are collected in the condenser should be condensed, okay. This is the actual function of the condenser, okay. Now porcelain pieces are also here, inverted funnel is here, and this is the solvent. When we provide the heat, it starts boiling, okay. Micro burner we have to taken here. Now you all know the elevation in the boiling point, that is delta TB is equals to T minus T0, okay. Molecular weight of the unknown solvent is, that is small m is equals to Kb into W upon delta Tb into W. Here small w is the weight of the solute, this is the weight of the solute, and this is the weight of the solvent. You all know delta Tb is the change in the boiling point or elevation in the boiling point, W is the weight of the solvent, and small w is the weight of the solute. All about this Cottre's method. By using this method, we can determine the molecular weight of the solute particle. Also, we can determine the elevation in the boiling point. Means we can determine the change in the boiling point of the solvent and the solution. Now, let us explain the next point of our syllabus. This is very important point, that is thermodynamic derivation of relation between depression in freezing point and molecular weight of the solute. Means we have to derive the one relation between the depression in freezing point. Here now we are considering the depression in freezing point and molecular weight of the solute. So for this, now we are considering the depression is freezing point. That means we have to decrease the temperature here. Now here this is two curves you can observe. This is AB curve, this is CD curve, okay. This is AB curve is of the solvent curve, and this is CD curve is of the solution curve, okay. From B to C the temperature starts falling down. Here also from D to C the temperature of the solutions falling down, and we have to plot a graph against vapor pressure and the temperature. You can see at this point A, initially the solvent in the liquid phase, and at point A it starts freezing, and that temperature is considered is taken as T0, okay. And at this point A the vapor pressure of the solvent is P0, okay. Now from this A point to F point the solvent starts freezing and it goes on solidifying, means at from the point A to F it starts freezing, and up to point F it completely freezes, that is, it becomes solid completely. Now at from and similarly in case of solution also, at point C it starts freezing. Okay, the temperature at point C is T and the vapor pressure is P1. Okay, now you can see the another point E in on the curve CD. The temperature is T0 and the pressure is P is considered. All about this is written here, that is at A solvent starts freezing, T0 is the freezing temperature of the solvent, P0 is the vapor pressure of the solvent. At C the solvent in the solution starts freezing, T is the freezing temperature of the solution, P1 is the vapor pressure of the solution. Therefore, now we can write freezing point of the solution is always less than freezing point of the pure solvent. So we can write the depression is freezing point is delta TF is equals to T0 minus T. And here P is the vapor pressure at temperature T0. This is the P at point E. This is the vapor pressure of the at temperature T0. Okay, let us see the next. Now we have to derive the equation. So here the quantitative relation between the depression in freezing point and the concentration of the solution can be derived thermodynamically by using Cauchy-Capron equation or Raoult's law. Okay, now here we have to apply the Cauchy-Capron equation, and there are we have to apply the Cauchy-Capron equation and Raoult's law. Okay, I'm applying the Cauchy-Capron equation to solid vapor equilibrium at point C of the curve, at point C at the curve of the curve AF. Now you can see this is the AF curve, this is A from F, this is solid to vapor equilibrium, that means at point C, this is the point C and this is point A. So we can apply the equilibrium here. We know that at point C, what is the temperature? Temperature is T and pressure is P1. At point C, temperature is P. You can see here temperature is at point C, temperature is P1. Temperature is P1 and vapor pressure is P1 and temperature is T. Okay, now the another point, we want P0 means at point A. At point A the vapor pressure is P0 and temperature is T0. The at point A vapor pressure is P0 and temperature is T0. Okay, now applying the Cauchy-Capron equation, ln P0 upon P1 is equals to Ls upon R, T0 minus T upon T0 upon into T. This is our equation 1. In your textbook the equation number 10 is written there. Okay, now this is our Cauchy-Capron equation, solid vapor equilibrium from A to C. On which curve? On AF curve. At point A the vapor pressure is P0, the temperature is T0. At point C the vapor pressure is P1 and temperature is T. Now here Ls is, as you see, solid to vapor is equilibrium is there, therefore that means naturally there is sublimation of the solid is occurs, and R will be the gas constant. Ls is the molar heat of sublimation. Now again we have another equilibrium, that is liquid to vapor equilibrium for the curve CD. Now we have the curve CD here, CD, CD for the solution. Now we want which point? We want point C and point E. Okay, what happens? We know that at point C the vapor pressure is P1 and the temperature is T, as shown in the graph. And at point E the pressure is P and the temperature is T0. This is on which curve? This is on the CD curve of the graph. This is the curve of what? This is the curve of the pure solvent, and this is the curve for the solution. Now, applying the Capron equation or Capron-Clausius equation, we ln P upon P1 is equals to LV upon R T0 minus T0 into T. This is equation number 11 or equation number 2. Now, here what happens? Liquid is in equilibrium with vapor. Means liquid is converted into vapor or vapor is converting into liquid. That means here LV, that is latent, this is the molar heat of vaporization we have to consider. Okay, LV is what? This is molar heat of vaporization. Now, we have to summarize this. We ultimately we have which equation? Equilibrium solid to liquid. So now equation 10 minus equation 11, we have to subtract this 11. We have to make the equation 11 equation 10 minus equation 11. Therefore, we have ln p0 upon p1 minus ln p minus p1. These two term left hand side equation. Okay, we have to subtract. Then in the right hand side equation, we have ls minus lv upon r t0 minus t into t0 upon t0 into t. Okay, now applying the laws of indices, you all know the law of indices. If we have ln x upon y minus ln y upon, or we let us consider this is z upon y, then it can be written as ln x upon y divided by z upon y, which can be written as ln x upon y into y upon z. Y get cancelled and we get here ln x upon z. Okay, in this way we got here ln p0 upon p. Okay, here laws of indices we have applied, and now here ls minus lv become lf, that is latent heat, or it can be said as molar heat of fusion, and we have lf upon r t0 minus t upon t0 into t. Okay, this is equation number 12. Now we have we know that T minus T0 is delta TF. For dilute solution, what happened? T0 is equals to T, and therefore we have this another equation ln P0 upon P is equals to P0 minus P upon P0. This is called as relative lowering of vapor pressure. Okay, now equation 12 becomes, applying this equation, we have P0 upon P. What is our equation 12? This is our equation number 12. We have to put the value of this. Okay, that is from this equation P0 minus P upon P0 is equals to LF upon R delta TF upon T0 square. Here T is equals to T0, therefore here written T0 square. Now, according to Rayleigh's law, the relative lowering of vapor pressure for a dilute solution is given by this equation, that is P0 minus P upon P0 is equals to N upon N. You know this, N is the number of moles of solute and N is the capital number of moles of the solvent. Now equation 13 becomes, only we have to put these values, LF upon R, this side, right hand side, delta TF upon delta 0 T0 square is equals to N upon N. This we only have to put this value. Now we have delta TF is equals to RT0 square upon F, that is RT0 come to this side in upon LF into N upon N. Okay, now let us suppose W is the weight of the solute and molecular weight is M, and it is dissolved in W weight of the solvent having molecular weight M. Therefore, M small n is equals to small w upon M and capital N is equals to W upon M. So delta TF is equals to our equation, this equation number 15 becomes delta TF is equals to RT0 square upon LF into W into M, capital M, and small m into W. Okay, how this is come, that is here W upon M and it is divided by, okay, it is divided by, therefore W upon M. Naturally, what happens, the cross multiplication will be takes place, W upon M into M, capital M, this is capital M upon capital W, this is the capital M. So we get here W M upon mw. Okay, in this way we got this equation. Now let us consider the next, that is, if 1 mole of the solid we have considered and it is dissolved in 1 kg of the solvent, what happens? We have considered the 1 mole of the solute and we have dissolved in 1 kg of the solvent, and that is W is equals to 1 kg. Then delta TF is denoted by what? KF. It is called as molar depression constant or cryoscopic constant. It is defined as the depression in the freezing point of the solution when 1 mole of the solute is dissolved in 1 kg of the solvent, and we get here therefore Kf is equals to RT0 square into M upon LF. What we have done, in according to equation number 16, we have to put these values, that is W is 1, this is capital M is 1, small m is 1, and capital W is also 1. So we get here what? Delta TF is equals to become here Kf is equals to what become? Delta TF is equals to become Kf. Okay, and so here we get Kf is equals to, this equation gives this is the thermodynamic derivation of molar depression constant. So thus by knowing the M, all this term M, R, T0, LF, KF, we can calculate this, all this term cap M. Okay, KF into W, delta TF into capital W. Okay, now this equation gives a relation between small m, KF and delta TF. Thus knowing these values, a molecular weight of the non-volatile solute can be calculated. Non-volatile can be calculated, that means delta TF upon KF is equals to M1. This is M1. Okay, what is M1? Small w upon M into W, capital W, is called as the molarity of the solution. This is called the molarity. This is M1 is called the molarity. So equation 20 becomes delta TF is equals to KF into M1. Okay, this is our equation. This equation gives a relation between delta TF, the molarity of the solution. It shows that delta TF is directly proportional to the molality, that is number of moles of the solute per kg of solvent. Hence depression of freezing point is a colligative property. Okay, this is our equation. This is delta TF. From using this equation we can determine the molality of the solute, non-volatile solute. Okay, this is all about the thermodynamic derivations, which gives the relation between the depression in the freezing point and the molecular weight of the non-volatile solute. Here Kf is the cryoscopic constant, where we have considered this W1 mole of the solute we have considered, capital W we have considered 1. All these things when we consider 1, that time Kf is becomes the cryoscopic constant. Okay, now in the next lecture we will study the next point of our unit number 5. Okay.